I'd like to welcome you to the next session here with Oliver Nicholas. He's from Uber, and I haven't heard this presentation, I must say, but he's basically working in the same kind of area as the last talk we saw in here on scaling Pinterest. They're just scaling Uber. And of course, we're really happy to have Uber in town, not as the cars, but
yeah, we're working on that.
As the lab. We have a couple of really cool tech labs here. Of course, we have a Google lab here that did all the V8 stuff, and now they're doing Dart. We've had some VMware cool stuff going on here for a couple of years, and now we have Uber as another really internationally interesting hotspot. So that's nice. It's not just Trifork doing cool stuff. It's also you guys like it. So, without further ado, I'll just let it over to you. Please welcome. Yeah.
Thank you. Yeah. So shout out to the Uber crew here. We're working on it. I think hopefully Copenhagen is next up, and then Aarhus soon thereafter. Okay. So my name is Oliver Nicholas, and the title of my talk here is Scaling During Hypergrowth. You'll actually I think find that it probably dovetails pretty closely with the talk before me. Not the least of which reason is that I think Pinterest and Uber both share some early employees who came from Yelp, where I came from before Uber, and so we've actually taken some of our methods to those other companies. So I think scaling under the sort of hypergrowth conditions is certainly an interesting challenge. The hockey stick, the exponential curves, but when you sort of reason about it, most of what applies that you want to be doing under hypergrowth is like in the sort of technology decision-making process. It really applies during regular growth as well, and it's there's some sort of sound principles that you want to apply that'll really help you, especially if you do get to that hypergrowth stage. So this is sort of that conclusion, really, is that it's much easier to grow if you've made smart decisions early on. It's really difficult to change the wheels on a moving bus once you get any reasonable amount of traction, momentum. And it doesn't really even matter how fast it's moving. If it's moving, it's really hard to do. So we're going to look at what's kind of universal from an early stage. And some of this is not so deeply technical. It's more about decision making. So who am I, and why should you listen to what I have to say on the subject? I'm software engineer and engineering manager by trade. I studied computer science, played with computers as a kid. The license plate on my car says Geek AFK. These are my credentials. I also do a lot of things last minute. So 2 months before I graduated from college at University of California in Santa Cruz, I decided I wanted to learn Ruby on Rails quickly. So I got in my car and I drove 600 or 700 miles from Santa Cruz, California to Portland, Oregon, and I took a weekend-long class from Dave Thomas, who's actually a speaker here at GOTO. So with my newfound Rails expertise under my belt, 2 weeks before I graduated college, I realized I should get a job. And so I did what people do, or at least used to do in the Bay Area, and I went on Craigslist to look for a job. And I found this little incubator called Uga Labs, and which was formed by this guy James Currier and Stan Chudnovsky, who had been sort of successful in some previous ventures. And I came down for this interview, and I discovered that Uga Labs was 4 guys in like an office, a room that was big enough for about 4 guys. And by the time I left, 2 years later or so, we had moved offices 3 times. We had grown to 16 or 20 people, and I thought I had a pretty good idea of what growth looked like. And so I went from UGA to Yelp, and at Yelp I was the 9th engineer. We were about 100 employees total. Yelp is very sales heavy. More than half of that was sales. And in the 5 years that I was there, we grew from 2 floors to 8 floors in this building. We dectupled in size. We did over 10x on our monthly uniques, which was going from maybe 6-7 million to about 80 million. At one point, like early on when I was there, I was literally the only engineer working on the front end for like www.yelp.com, which was cool at the time. And then by the time I left, there were like 200 engineers in the company. So as you can imagine, by that point, I like thought I knew what growth looked like. I thought I had a good sense of this. And then I came to Uber. And at Uber, I was sort of hired on as like the second engineering manager. I interviewed in August in 2012, and there were 18 engineers. And then when I started, like 2 months later, I took a couple weeks off. When I started 2 months later, there were 30 engineers. And I was like, what happened? Like, this wasn't the team I thought I was joining. So in the 2 years I've been there, we've gone from 100 employees to nearly 1,500 employees. We have about 250 engineers globally. I can't say what our exact traffic growth looks like, but if you take the 5 years of Yelp and squish it down into 1 year, it starts to look like what Uber's growth looks like. So now I really think I know what growth looks like. So just for those of you who aren't familiar, since we're not anywhere in Denmark yet, much to our collective disappointment, what is Uber? We're an app-based service that connects riders with transportation options. So you open the app, it shows you nearby cars. You hit the button to request a ride. You get sort of an automatic algorithmic dispatch to a driver who can accept your ride. They'll come pick you up. They will take you where you want to go, drop you off. You get out of the car and walk away. You have a credit card on file. There's no fussing with tips or paper money or anything. You just walk away. It's pretty awesome. You feel like a boss, and it's really convenient. And on the back of that, we've sort of grown to 200 plus cities in the last 3 years. So what my team in San Francisco and the team here in Aarhus build is the sort of back-end services that this mobile app talks to. So Uber was founded in 2009 in San Francisco. We put cars on the road in 2010. To date, we've collected over probably close to $1.5 billion in funding. And then most of our employees are not in headquarters. Certainly most of them are not here in Aarhus. They're out in those 200 plus cities running operations locally. And we're hiring here in Aarhus if anybody's interested. Okay, so that's why you ought to listen to me. Why should you maybe not listen to me or take what I say with a grain of salt? I was like a poor student in high school. I was too busy like programming at home to like pay attention in school, and I haven't been doing this for that long, and neither have I managed to read a full book this year. But I've spent a fair amount of time with sort of successful startups and less successful ones. So I've seen a bit of that life cycle, and I've made and witnessed a lot of the mistakes that that can be avoided. And I don't know much about big multi-thousand person companies. Every day I work at Uber, it's the biggest company I've ever worked at. In fact, when I went to interview at Uber, I was discussing it with the CEO and the head of engineering, and they were asking me, why you leaving Yelp? And I was like, well, it sort of seemed like it was time to go. We got to 1,000 people. It was big enough for me. I was like, I'll help you guys get to 1,000 people, but when we do that, it might be time for me to go. And I've had to eat my words. I've had to hope that they don't remember that conversation, because that happened way quicker than any of us were expecting, I think. Okay, so let's dive in. What is the most important thing to keep in mind if you're scaling an engineering team? Is it having enough servers? Is it having enough RAM in your servers? Is it which language you choose? It is none of these things. It is you need to have a wiki. You need to have a place to put your institutional knowledge. You will not survive without this. This becomes where everything that's important gets written down. You put run books here, postmortems, contact numbers for your coworkers, emergency information, your office public IP address, your how-tos, your how-not-tos. Over time, almost any question that gets asked ends up being addressable by the wiki. The answer becomes check the wiki. Doesn't matter where you host it. Make sure you have backups of it, and it actually matters a little bit where you host it. It matters that it's not on if this is what documents your failure procedures. It matters that it's not on the same infrastructure as the thing that has failed. This is something that I've done wrong at 2 companies now, and so it's an important thing to keep in mind. So this was interesting. I came to Uber. You know, they were 2 years into the thing, 30 engineers, and there was no wiki. And so this is like this is something that it really pays to start building early on. It'll help you onboard new employees quicker, and it makes sure that everybody's kind of on the same page, so to speak. Okay, so what is the second most important thing to scale an engineering team? Also, maybe not what you think. It's not the servers. It's not the RAM in your servers. It is the people that you have at your company. Effectively, this is your most important resource. One engineer can only write one engineer day worth of code in a given day. And so if you want to squeeze that to 2, you either have to get 2 people, or you have to feed your one person like those drugs that they feed fighter pilots to keep them up for 36 hours. But that's obviously can only go so far with that. So the thing is that people actually become your primary constraint pretty quickly. It is if you're doing the right thing, if you're hiring, if you're being really rigorous with your hiring and you're not making any compromises, it will be very difficult to find really good people, and you should not make compromises, especially early on. Good people beget good people. They will hire other good people. They will help you. They will help you always improve the quality of the staff. And this is really important to do early on. It's hard to overstress how easy it is for this to go wrong. So you want these A players, you know, people who are there to, you know, who won't mind they're at the bar and it's the weekend and something, you know, the site goes down, and they, like, without you asking them, they'll have their laptop and their MiFi with me, and they can get online and they'll start fixing stuff, or they got the SSH client on their cell phone, and they'll be on the dance floor and they're like debugging stuff. These are the people that you need early on. This is you can't get around this. If you have a site and you want it to stay up, it's not going to, I promise you, and you'll need people who are cool with that and who are cool with really sacrificing some of their time to help achieve that. These are people who prefer getting their hands dirty. You want to hire generalists. Generalists will help you keep your headcount low. It'll help you avoid needing to hire more people. They can dive in anywhere, and this is pretty important. You can't get to the point of hypergrowth if you run out of money before you get there, because you spend all your money on people who are kind of doing like half a job. And so if instead you can hire people who will do 1.5 jobs, you'll be in a great position later down the road. So people can fill multiple roles. But obviously that comes with a caveat, which is we wouldn't want to hire a generalist to do something really very specialized. So you have to balance that there. It depends on your problem space. And then you really, on the subject of people, you really need a people person. If you are like if you're a founder or super early employee, and you don't have like a people person, and you're just one of those people you like to put on your headphones and write code. If everybody at the company just likes to put on their headphones and write code, you can very quickly run into a situation where nobody's really addressing the kind of like softer side of issues that arise. So somebody who like can sort of elicit emotional responses, can have those important conversations with people, can be really valuable. It's entirely possible that if you get a staff of, let's say, 10 people, you could easily end up with somebody who's like maybe not like sort of pulling their weight, or isn't really engaging, or doesn't quite understand what's going on. And without a people person, like there may not be anybody to surface that information to you. Like it's entirely possible for that to kind of be difficult to see. So this is important. You got to make sure you have one of these people persons. Okay, so we have successful sort of we have a wiki to put our stuff in, and we have people to build our product. What else do we have to talk about? The next thing to talk about is failure. When you are scaling fast, or really even when you're not, things start breaking. This is a fact of life. The sooner that you accept it, the happier you will be. This will always come to bite you, and you can work around it. You can be prepared for failure. So this picture here is a wine rack that I built. It was sent to me in the mail, and in pieces, and I like put the pieces together. You may notice something kind of weird about it. Something doesn't quite seem right with it. I did not build this thing correctly. I failed horribly at building this wine rack. Was that? It could. Yes. Yes. I guess it would work as well in space as if it were built the correct way. Yeah, it's a fair point. But I was prepared for this. I didn't panic. I noticed the problem before I committed too deeply to it. I rebuilt it. I don't have the corrected picture here, but I did fix it. So failing once is okay. In fact, or failing at failing at different things once is totally reasonable. You should expect this to happen. It's even to be expected or supported. Failing at the same thing repeatedly is usually a bad sign. If you don't want to get known for this, you remember like the Twitter fail whale, like Twitter kind of got famous for going down all the time. This is not a great situation to be in, and so if you break your wine rack, write a postmortem, document your learnings in the wiki, and then the next time will likely go much smoother, and you can avoid repeating your mistakes. So we have even if you have a team of fantastic engineers and you yourself are a perfect engineer, you still have to design for failure. Even if you're like the best they come, like you still have to design for this. And the reason you have to design for this is because even failure-proof things will fail at some point. Your data center will absolutely fail you. Like it's great to have redundant power feeds to your servers, but if a plane crashes into the power line right outside of the data center, it won't do you any good. Like you will lose power to your whole data center. The servers will fail you. Redundant power supplies, redundant network connections, RAID disks in your servers are great, but if like a data center tech like pours coffee on the server, like it's not, or like walks by and unplugs it, it's not gonna help you. Your database will probably fail you. Databases are super complicated. It's like hard enough to explain how they work. It's like really hard to explain how they fail, and it's almost impossible to fix them when they do. And your own code, or other people's code will almost certainly fail you. There's this Brian Kernighan quote, debugging is twice as hard as writing the code in the first place. So if you write code as cleverly as possible, you are by definition not smart enough to debug it. This has probably hit all of us at some point. There's another one, I can't remember the line exactly, but it's like something about the amount of time that passes between when you're unable to distinguish between code you wrote and code that somebody else wrote. You put down a piece of code for a couple months, you come back to it, and you're like, "What was this idiot thinking?" And it like turns out it's yours. Your people will fail you in some ways, in ways you maybe don't expect, but also people burn out sometimes, or people just sleep through their alerts in the middle of the night. This happens all the time. things will go wrong. And in some ways, this all becomes true or more true over time. Any of you like have things hosted in AWS? Nope, none of you. Well, if any of you do, you would have just gotten an email from Amazon, like in the last week, telling you that they're about to reboot half of your servers. So even things you thought you could rely on, you can't always. So you should be designing for failure, because even if it doesn't happen when things are calm, it will almost certainly happen when hypergrowth or any kind of growth kicks in. If there are edge cases, if there are 1 in a million chances, those are going to get found, and they will happen. There's this Woody Allen quote: "If you want to make God laugh, tell him about your plans." So it's not just enough to like design for failure. If you want to save enough stress to add a few years to the end of your life, you should just start expecting it. Just be happy when it happens. So plan for it. If you think that's too pessimistic, then plan for success. Then plan for your plans to fail. So you can spend you can spend months designing like a system that you think will perform well, let's say under load. It probably won't. So you don't just flip switches with no way to go back. If you want to hear about how that can go wrong, talk to an engineer from Dig from the website that when they did their V4 launch. If you burn your bridges and have no way to go back, it could be a pretty scary situation. So in the old days, we spent a lot of money on like really fancy hardware that was supposedly was like really stable, but it would still fail sometimes, and you would just be really upset when it did fail because you weren't expecting it to, because you'd spent all this money on something that wasn't supposed to fail. In some ways, we've been trying to internalize this in the industry for a long time, and I mean it's been much longer than just this. But you know, RAID, redundant array of inexpensive disks, as it was like originally known. That's a concept, or that was named in 1987. So we've been at this a long time, but it's actually in some ways taken a long time for us to kind of accept that through the stack, and to really expect it in our application designs and down from there. So something to point out: tests won't save you here. You can't design around this. Good testing and staging will reduce your development time, catches bugs, but it won't prevent failures. There's just no way to do it. So expect it, you'll be happier for it. So how do we build a failure resilient architecture? There's a lot of things that we could talk about that would be very specific to, let's say, what Uber has done, or what any other organization has done. Those are very specific to like particular problem spaces. I want to talk about some sort of generically useful points that are kind of applicable everywhere. What you want to do is we want to minimize failures with redundancy, and we want to minimize the impact of failures that happen anyway by isolating our systems from each other. And then we want to spread out our operating surface so that one failure doesn't take everything down. So even if you aren't building data centers, and very few people are anymore, it's really important that you have disaster recovery plans. You have to geographically distribute your your operating base. Redundant AZs that are far enough apart that not necessarily a giant life-ending meteor, but if for instance, Uber is based in California. California is really prone to earthquakes. It's not unlikely, that at some point in the next 100, 200 years, like a major earthquake will come through. And so you really need to have geographically distributed centers of operation so that if something happens, you are prepared. I mean, there's other things that can happen that are far more likely than a meteor strike or an earthquake. There's power outages. There are all sorts of accidents that can happen, and then there's stuff that happens even outside of there, right? The internet is a complicated web of a place, and internet routes can kind of just stop working. You want to have a way to to route around that. So the naive implementation here that's totally reasonable is sort of just a failover architecture, right? You have a hot master data center, and then you keep some read slaves in your other data center, and then if the master goes down, you just flip over your DNS, promote your masters, and and you're good to go. You're riding another data center. And then from there, you can sort of get into some of the stuff that, for instance, that Uber is getting into with trying to run active out of multiple data centers at the same time. And this is something that's really encouraged, I think, by the design of things like Amazon's EC2, where you sort of assume that maybe individual components, individual nodes are less reliable, network connections are less reliable, and it sort of encourages you, I think, to build these more redundant systems. So you also have to design for failure at your server level. Just by default, you should have rated disks so that losing one disk doesn't ruin your day. You can isolate yourself from having a ruined day really easily. And you have to have backups, hot backups of your databases, and you have to be testing this promotion process of flipping over from master to slave. It doesn't do you any good to have these if you don't know what to do when the system goes down. And it also doesn't do you any good to have it if, or it doesn't even do you any good to have tested it if the procedures for it are on your wiki that were on the infrastructure that just went down. So, so write a runbook, have a runbook section of your wiki, and put this stuff there. And then you really want to distribute these things. You have to realize that sort of every unit of functioning, every piece of hardware can fail, every kind of functional unit can fail. So you want to distribute these things across racks so that rack failures don't affect you. And then if you can, you want to put dual NICs in your servers so that even that top of rack switch failure doesn't actually take anything down. So what we're doing here is we're assuming that anything can fail, and then we're adding one extra layer of redundancy so that if it does fail, it doesn't actually take anything down. But we're going to design it. We want to design it all the way through so that even if it does take out that one server or that one rack or that one data center, we can still continue operations. So you also want to design for failure at the service level, the process level. You want your processes stateless wherever possible. You really want to maintain state in sort of separate systems. You want to be able to shift around worker processes, right? If you have one big database machine and 10 service machines, app machines, the likelihood is that one of those app machines is going to fail first, and so you want that to be as low impact as possible. And then you need to assume that everything that isn't your in-process code is unreliable. Anything that goes across a process boundary can fail. Anything that's even in another thread in your process can fail. The disk on the server is pretty reliable, but maybe not. And then anything that's across a network boundary, you may as well be sending mail to Somalia. You have no idea what's going to happen once you start going out across a network. So you make sure you got timeouts on these things. You make sure that you're essentially prepared that kind of any one of these systems can fail. If you have a job queue at Uber, we run Celery, which is a Python process or a Python system. There's also Gearman, there's a few others. If you have jobs in this queue that talk to a third party, and that third party, their service goes down or randomly gets slow. What's going to happen is each one of your workers is going to it's going to chew up normal processes and it's going to get to this process that talks to this dead service, and they're all just going to back up, and then suddenly your whole queue just stops processing anything, and then you end up with this big backlog, and it's just it's this failure of your system, and so you have to isolate and segment your code that relies on external systems. And this is something to keep in mind if you're doing something like implementing Facebook login or something, right? I think it's considered really reliable now, but certainly in the early days, it actually wasn't. And so suddenly you have the system where nobody can log into your website just because this external third-party system is down. And so along those lines, you really want your functionality to degrade gracefully if something isn't accessible. I think they've talked about it a bunch, how on the Amazon web homepage, which is they have a very sort of service-oriented architecture, if each box on that page is a call to a different service, and if one of those subservices, and each of those subservices has a defined SLA, and if one of them doesn't return within that defined SLA, a couple hundred milliseconds, you just don't see that box on your homepage for that load. And it's like, meh, well, whatever. It's, it's a slightly degraded experience, but the homepage still loads in some set amount of time. So along those lines, you really want this service-oriented architecture. This is, I think this is a concept that's has been gaining steam for a lot of years now, and it's sort of time. It's like these old monolithic systems are and ought to be sort of falling out of favor. Having one big code base is awesome for a bunch of reasons. Refactor is really easy. Everything's in one place, and you don't have to deal with Git submodules or whatever. But having 100 engineers work on a single code base is a total nightmare. After a certain point, you can forget about daily deploys. And if you want to like really frustrate your early engineers and convince them to leave, you tell them that they can only deploy once a week. This is like when you go from being able to just like deploy whenever you want to having the schedule and all that stuff, that gets really frustrating for people. I mean, in a truly large scale, if you get to like Facebook or Google size or something, good luck. But even your version control system probably starts failing on one giant code base. Both Google and Facebook have had to essentially rewrite, Git, Mercurial, whatever, or Perforce, whatever they've been working with, to work efficiently with that many people on the same code base. So the great thing about a service-oriented architecture is that it helps you stay agile. So there's less concurrent development on any one code base. There's quicker refactors. If you have smaller deployable units, smaller services that you're pushing out, there's fewer change sets going out at any one time. So fewer things are shifting around. And that means that they can affect fewer features. So your outages are more contained. You get better defined areas of responsibility so that you don't, instead of there's 5 people on your team and they're all responsible for everything, there's like 1 or 2 people on each section. And then you should definitely get a good code search tool in place. Super important. If you've got 50 repositories, like how are you going to find anything? So on the subject of service isolation, you need to assume that any one of your services might fail. Yes, they're all on your own infrastructure, but those process boundaries are no good, those network boundaries are no good, and you're deploying these things all the time. So at any given time, one of them might go down. You also want to separate critical functions into their own services. This actually lets you kind of treat your different services with different levels of importance. So at Uber, we've actually divided our entire architecture into two broad areas. There's the real-time system and there's our backend system. So when drivers are driving around and they're pinging back their location to our servers, that's all going into this real-time system. When I open the app and I see the nearby cars, that's all from the real-time system. When I request a ride, real-time system. As we're on that ride and the system is sort of keeping track of where we're going, that's in the real-time system. And it's not until we get to the destination, hit that end trip button, it's not until the driver ends the trip that the real-time system, which by the way, hasn't stored anything in like a relational database, hasn't touched a relational database this whole time. There's a bunch of stuff in memory, there's stuff replicated between different in-memory processes, but nothing has really been written down. There's some logging, but nothing's really been written down. It's not until all that's done that package of information gets put together and sent into the backend. And on the back end, and it's actually it's sent through a couple of queuing systems so that it doesn't get lost on the way, and then it gets processed, written down into a database. We do our billing, we send you a receipt. What that means is that our entire backend, our database can go down, and the core functionality of Uber still works. And so that lets us be much more kind of agile with that backend system. We can deploy whenever we want. There's still maybe a degradation of some pieces of functionality if the backend or some part of the backend goes down, but it lets us be very agile with that code, and we only have to be kind of this next level of protective with that real-time code. And even then, we segment that by city, and so we can be really safe with that too. We can deploy to a really small city, and then go to a bigger one. So. this is all really important to do. You're designing for failure, you're expecting for failure, and then you're just like, well, whatever, and you go to sleep. Well, the problem is that you have to know if a failure happens. And by definition, at this point, the failures that are going to happen are going to be the like unknown unknowns. You've prepared for all the things that you think might fail, but there still are going to be things that are going to fail outside of that. So you can't be blind when that happens. Okay, so even with good design decisions, you're going to experience failures. And you want to know when that's happened. And so the only way to really do that is automated monitoring and alerting. And then the problem is that not all failures are obvious. So something can go from responding in 100 milliseconds to responding in 10 seconds. It's still returning 200 status codes every so often, but it's actually gotten a lot slower, and that's like as good as a failure. Your system may as well be down. It's really not working, but you might not know about it because you're still seeing good status codes come out of it. So my philosophy here is that you have to track everything, even stuff you don't care about, because you never know when you're going to start caring about it, and then it's really nice to be able to go back and say like, oh yeah, we have this data. It's buried in our log somewhere, but we have it. The only problem here is that this requires like an investment because by definition, this is going to be higher volume than whatever's coming, or at least equal volume to like the number of requests coming into your system. I mean, at minimum, you're talking 4x of what comes in. You got an access log entry from your web server. You have an access log entry from your application itself, and then you're sending out a time series stat for each one of those things as well, because you really want to measure things at each section in the pipeline. Because if something's failed and you have 4 processes, there's a web server and an HA proxy and an application server, like how are you going to know which place it failed at? You have to be measuring each one of these so you can see where the drop off is. And I think if you do this right, you might be at 10x. For every one event that comes in, there's 10x that go into your logs and event systems, if not more. So the first aspect of tracking everything is logging everything. You log everything, but like really just almost everything. Don't ever log response bodies or post bodies from HTTP requests. Your engineers will ask you to do it. They'll say, "Hey, can we just get that data? We'd really love to see what's coming out of the server. It would be really helpful." Don't do it. Don't do it. It's a trap. I guarantee you, if you do this someday, somebody is going to log credit card numbers or passwords into your logs, and then you, if you're the responsible person in the org, will spend your weekend writing code to like filter credit card numbers out of logs, and then you'll spend your Saturday doing that. Then you'll spend your Sunday running that code on all of your logs, so you can scrub out all of this sensitive data because it's stored in S3 for all time, and you can't leave credit card numbers there. This is not a fulfilling way to spend a weekend, and so I advise you to just not log this stuff at all. It can be very helpful. It could be really helpful to have. But to just do it in a blanket manner is really unwise. You can add spot logging where you need to, but this is just this one area where you just can't. Just as a rule, you shouldn't write everything down. Even if you don't log these post bodies or response bodies, somebody will still find a way to put credit card numbers into your logs. I promise you. I've seen it a million times. I've seen it like 5 companies. Like people will do this. Something we've done is you write a little. All your logging goes in through one method, right? So you write a little filter in that login method that looks, does this look like a JSON object? And does it look like it has a field called credit card number? Or does it look like it has a field called password? You can write an Nginx module that actually looks at your response bodies and looks for 16-digit strings of numbers and then does the LUN checksum check and says, is this a credit card number that we're sending out? And then you can throw an alert or block the response or something. What you want to do is make it impossible for you to screw some of these things up. And this is something that you're probably unlikely to take advice on like up front. If you're building a Hello World Rails app, you're not really likely to. This is necessarily a big concern, but remember this like the first time it happens, and then you can prevent it from happening again. Right? You write it down in the wiki. Like, oh, that's right. We have to be proactive about not not accidentally storing sensitive information, and then you do something about it. Aggregate your logs. Don't make people go onto your application servers to get the logs off. You really don't want people as a rule. You don't want them going onto your production infrastructure just to do debugging or to just to get pieces of information. You kind of want that all segmented. You want to keep your production infrastructure secure, and you want to keep it intact, really. There's lots of good stuff for doing this. At Uber, as at Pinterest, we're big into Kafka, but there's Scribe, Flume, Logstash, all sorts of stuff. You want to make your logs searchable easily, and I suggest putting them all on S3. S3 is cheap. It's an easy place to put them. You can run MapReduce jobs on them. This is a good way to do things. Okay, you also want to graph everything. Emit stats into your real-time graphing system. The funny thing about this is you can run into problems with this too. All you're doing is emitting stats. Like, what can go wrong? Turns out that if you're using TCP to send these stats into your stat aggregation system, and your stat aggregation system gets overloaded, it'll actually start, and you're sending these stats like in process, it'll start slowing down your application. Your application will get slow. It will serve slow responses because it's trying to inform you about how many responses it's serving. This is like a really unfortunate situation to get into. So do these things out of process. I mean, same thing with logging. You want to try and remove anything that can get slow, that's high volume. You want to make sure that it's isolated somehow so that if it backs up, it doesn't actually degrade performance in your main application. And then put your useful dashboards that you have, put those in your wiki, and then this becomes your primary system really for triaging kind of degradations of service. What's going wrong? Oh, well, I've got this sweet dashboard that shows me response times at every part of the system and to my external calls. And that way you can really pinpoint where things are going wrong. At Uber, we use Graphite for this. At Yelp, we used a front end I wrote called Firefly. They both kind of suck in their own way. So if you can come up with the killer app for the system for operations teams, that's a $1 million idea right there. Okay. You want to monitor everything. So you've got your stats coming out, and you want to make sure you're keeping track of what those stats say. You have to know if something has gone wrong. So relentlessly add monitoring. At Uber, we have tens of thousands of monitored things. In Nagios, we have tens of thousands of alerts that can go off. We distribute them among teams where we can, but we never shy away from adding a new one. And this has been the primary thing, I think, that has improved our uptime and reliability in the last couple of years. Use PagerDuty. PagerDuty is an awesome way to like share the responsibility and do alerts along these systems. But it's funny because PagerDuty can go down also. And if your system goes down while PagerDuty is down, you won't get an alert about it. Or one of your engineers, like the new guy who joins the team, can forget to set up a notification rule in PagerDuty, so they don't have their phone number there. So it sets off an alert, but doesn't actually send them a push notification or a text message or anything. So you have to actually write code to monitor that to make sure that that's taken care of. It's totally inane, but you have to do these sorts of things to make sure that nothing falls through the cracks. And then when things do go wrong, write a postmortem, put it on your wiki, add more monitoring. So the great thing about tracking everything is that it lets you move faster. Okay, running a little low, but on time here. But we're sort of prepared for failure. Let's talk about just some choices to make. Use boring things. This is my best suggestion. Don't get creative where you don't need to. I think Nginx might be the newest, most like radical piece of software we use at Uber. Not entirely true, but in the back-end section of things. Remember, like hiring people is going to be your primary constraint. So if you're using new stuff that not many people use, you're going to have a harder time finding people who are experienced. You can find people who want to learn it, but you're taking a risk there with newer platforms. So the rule of thumb here is don't take those risks where you don't intend to do anything interesting. If you're just serving, web pages, don't pick an interesting web server. Pick Apache, pick Nginx. So at Uber, a couple of years ago, we chose Node.js as this real-time platform component. the backend was in Python, but we chose Node.js for this real-time system. And Node was actually a decent choice there. This system is lots of concurrent connections, lots of time just spent waiting for network I/O. But it was like alpha software at the time. This was a totally crazy choice. It's turned out fine, but you have to be careful of that. Where Uber did not get creative was its database. We chose MySQL for the database. Like, there's no reason to innovate there. We just want to store data in it. Let's not get too excited about it. We did once do something crazy. We migrated from MySQL to Postgres. Literally, like, wheels, moving bus, the whole thing. Like, it was amazing. It was pretty awesome to watch. Total disaster. we're still in the process of undoing some of the mistakes and some of the problems that arose because of that. Then you want to choose the right tool for the job. For instance, Node was the right tool for the job in that case. You also want to make sure that, like, when you are storing things in your database, you separate out your online and offline workloads. It's a total mess to try to make one system service like online transactional requests, a new transaction, we made some money, and then to have that same system tell you how much money you've made every month for the last 10 years. Like, that's a totally unfair thing to ask of one system. So you want to separate those workloads as early as possible before the data gets truly large. Okay, one other really important thing is you want to be secure. I'm going to skip over most of this, but you want to, this is a funny one, this encrypt and obfuscate primary keys that you show to the front end. If you meet with any amount of success, you do not want your competitors figuring out how many new users you're getting just by creating a new user account once a week or once a day and seeing how the primary keys increment, /users, /5, /users, /10. This has come up everywhere I've worked. It's really funny. You don't think about it in the beginning, and then suddenly you're like, oh, we're doing okay. And then the boss comes by, and he's like, why are we telling people how fast we're growing? So it used to be that we'd, like, encrypt the IDs because you were space conscious. Now just use UIDs for your primary keys. There's all sorts of other stuff you can do here. But I want to get to the next point, though, because it's my last slide, and it's pretty important. Create frameworks. You want to make doing things the right way really easy for your engineers. So at Uber, we have Clay and we have Play-Doh, and those are the Python and Node.js frameworks, respectively, that we've built in-house. And what those are actually, Clay is built on top of Flask. So it's Flask is a Python HTTP sort of micro framework, and Clay is some extra Uber code on top of that. And what that does is gives you easy hooks into the database, easy hooks into the logging system, into caching, into monitoring, alerting, analytics. What you do is you make it so that the path of least resistance, the easiest thing to do, is do things the right way. Do things the way that the people who have set up those systems have prescribed. Otherwise, if you start growing really fast and you don't have things sufficiently documented on your wiki, everybody's going to invent their own way to do it, and you'll end up with this crazy infrastructure that nobody can reason about because there's no homogeneity. This is how you propagate your cultural norms as you start to grow. You just make it so that's the easy way to do things. Okay, so what do we need to do? You need a wiki. You got to hire gritty geniuses. Sorry, but you just have to figure out a way to do it. Pick boring technology where you have no intention to innovate and resist the urge to try everything new or refactor everything every month. Expect that everything will fail and that it may not fail in obvious ways. You want to reduce your statefulness so that when there are failures, the likelihood is that it will not affect a system where it matters that much. Track everything, keep your system secure, and code all of these best practices into some technological system that is really straightforward for your engineers to use and gives them the sort of easiest path to success. And that's all I got. Thank you. Any questions?
Yeah, we do have a few minutes for questions if there's some, but it doesn't look like anyone came up in the app.
Can you elaborate more on the choice why you were trying to migrate from to post?
Oh man, I was afraid somebody was going to ask that. Yes. Well, actually, the original choice was based really on two big features in Postgres. One was online schema changes, like first-class online schema changes. So the ability to add columns or add indexes online without taking any downtime. As it turns out, that's like it's true mostly for indexes, but it's not always true for adding adding columns to tables. You know, Postgres has a fixed size memory space that it uses to describe a table, and if you're adding a column and it requires going past that boundary, you actually then have to rebuild the whole table anyway. So it doesn't even work all the time. But that was one of the big ones, right? Having to take downtime or lock tables in order to do schema changes is really frustrating. And if you're growing fast and you're adding new features and functionality, you're going to be doing schema changes all the time. So obviously for MySQL, there are tools. There's PT Online Schema Change, and there are now pretty well developed tools. But it's like first class support in Postgres. That was one of them. The other one was that almost everything that Uber does, almost every piece of data that comes in, has a latitude and longitude associated with it. And MySQL has really poor tools around geospatial data, and Postgres has nearly first class support for geospatial indexes. And we wanted to be able to do a lot of querying around that. But that's actually that's really my main point there about the separating your online from analytic workloads into separate systems. What we kind of failed to really to encode there was that those geospatial queries we were doing were really like analytics things. Those were things we did after the fact to gain insight into the system. And the better pattern there would be to ETL those, to copy that data into a system like a Postgres database that did have those geospatial indexes, but we didn't necessarily need that functionality in the main database. So our problems with Postgres are around scaling concurrent connections. The authors of Postgres tell you really only want like 1 or 2x the number of cores on your box, that many concurrent connections, which is nowhere near enough for like a sort of single master setup. And we have managed to tune a Postgres instance with 64 cores to like 400 concurrent connections, which is like sort of unheard of, and we're always it's always a little terrifying, but it works well as we're kind of sharding out the systems and coming up with more creative ways that are ultimately more scalable anyway. But we've been forced into that sooner than we would have been otherwise by choosing a database that in the end doesn't actually support like sort of the kind of growth that we needed that well. Obviously, there's lots of opinions about Postgres, but yeah. Anybody else? Cool. Thank you.